graphically, adding and subtracting them graphically. First off, J.R. Argand developed a method for displaying complex numbers on the coordinate plane, essentially making the x-coordinate the real coordinate, real numbers, and the y is your imaginary. Therefore, 3 plus 4i, you go out 3, up 4i, and there's that number. 2 minus 3i, out 2, down, there's 2 minus 3i. Now, you don't need the arrows. I'm using the arrows to point to the numbers. Negative 4 plus 2i, I go out negative 4 on the real, up 2 on the imaginary. There's that number. 3, which is really just 3 plus 0i, is simply right here. 4i is simply here. Again, you don't need those arrows. I'm just pointing to the places where these are found. Now, the absolute value of a complex number, like any number, it is the distance from 0. So when you're looking for the absolute value of a plus bi, think of a triangle. This is 8 units on the real axis and 6 units on the imaginary. We don't use the I. The absolute value is the distance this point is from 0, and that's a real distance. It's a right triangle, so again, we're using Pythagorean's theorem. We've been using that a lot. We used it with the Pythagorean identity when we did trig. We're using it here. 8 squared plus 6 squared. Thank your geometry teacher for being able to figure out that the square root, that winds up being 100, and the square root of 100 is 10. Let's look at a couple of these. Find the absolute value of each complex number. Well, this is the one that we just did, and here's the work. To the right is the triangle. Come down and look at the next one. Try it. Again, try graphing it and then finding the absolute value. Notice there is no I in the absolute value. Here's the graph. Here's the work. The point 2 minus 3i is the square root of 13 units away from the origin. Another one. Negative 8 minus 15i. Pause the video, try it. And now that you're back, let's take a look at it. And if you need to, remember that we would go out to negative 8, down here to negative 15. Here's the point. Here's my distance. There's my right triangle. 17 units away. Negative 8 quantity squared, negative 15 quantity squared, square root of 289. The absolute value of a complex number is simply the square root of the real portion squared plus the b, the real part of the imaginary unit, squared. Here's another example. 2 minus 3i, here's 2 units out, 3 units down, here's the point. 2 minus 3i. I can draw my triangle. Here's my 2, there's my negative 3, here's the square root of 13, my right triangle. Determine the absolute value of these. Okay? You will have to do this on a test or on a quiz. Pause the video and try it. Okay, take a look. How did you do? There's the 4 minus 5i, square root of 41. The absolute value of 7i? 7. That makes sense. It's 7 units straight up, so it's 7 units away. Negative 2i, that's 4 plus 1 is square root of 5. 1 plus 3i, here's my point. It's square root of 10 away. And finally, we have 6 plus 0i. It's 6 units away. Negative 7 minus 3i. If I'm just plotting the point, I'm plotting this point. I can draw the triangle to help me figure out my distance from 0. Well, that's 49 plus 9. The square root is the square root of 58. Solving a quadratic equation under the set of complex numbers. Remember that the discriminant helps us to figure out what type of solutions we have. When I solve a quadratic equation under the set of complex numbers, I have ax squared plus bx plus c equals 0. The discriminant is equal to b squared minus 4ac. When d is greater than 0, solutions are real. There are two solutions that are real. When d equals 0, there's one solution that is real. When the discriminant is less than 0, no solutions are real. Two are complex. Complex always comes in pairs. If I take a look at this, if I want to solve it, I have x squared is equal to negative 11. X is equal to plus or minus the square root of negative 11. I don't leave a negative under the radical. I bring it out. So x is equal to plus or minus I root 11. Okay, on this next one, over here on the left, we got our answer. This one I can't factor and I can't solve using square roots, so I'm going to need to use the quadratic formula. So x is going to be equal to negative 1 plus or minus the square root of 1 minus 4 times 1, that's a and c, all over 2 times a, which is 1. This is negative 1 plus or minus the square root. 1 minus 4 is negative 3 over 2. I don't leave the negative 3 underneath the radical. I have to bring it out. So I have negative 1 plus or minus I root 3 over 2. My complex solution. This is a complex solution. Complex solution. And this one over here is pure imaginary. Now remember that I can write an imaginary solution as 0 plus or minus I square root of 11. So I can write it as a complex number. Any number can be written as a complex number. We'll do some more solving of the complex numbers in our next lesson. For the summary, a complex number is any number that can be written in the standard form a plus bi, where a and b are real numbers and I is the imaginary unit. Here's some examples. 7 plus 2i, 7 is a, 2i is the bi part, with 2 being the real, I is the imaginary, and so on. An example like this one can be broken apart to negative 2/5 plus 3i over 5. I have my real and I have my imaginary. You have to be able to identify both the real and the imaginary portions of a complex number. The set of real numbers and the set of imaginary numbers are subsets of the set of complex numbers. And that's it.